As you recall, earlier in this chapter, we talked about estimating the value of a summation of a convergent series of positive terms. And we went through quite a process to talk about that. Well, and now that we have alternating series where our terms alternate in sign, they're not positive terms, then we need to revisit the idea of estimating the value of a series, an alternating series that does converge, and see if we can estimate the value within any accuracy that we choose. So what we're going to do here is we're going to start with an alternating series that we know is convergent. In fact, the two conditions are true, that the limit of the a sub n's is 0, and the a sub n's get smaller. The a sub n's get smaller. A sub n plus 1 is smaller than, less than or equal to a sub n. Okay, so the further we go, the smaller the a sub n's get. So that's what we start with. Now, we're going to define, now we know that the series is convergent, and so we're going to define the sum to be the value of that series. Okay, we're going to, S to be the sum of that series. And while we're at it, we're going to define the nth partial sum, S subscript capital N, to be the sum of the first n terms, capital N terms. So we're adding up the first capital N terms. So if we had S sub 4, then we'd be adding up the first 4 terms, the 1, 2, 3, and 4th term, and so on. Now, we're going to define R sub n, which is called the remainder, R subscript n, which is called the remainder, which is nothing more than the difference of the actual sum. See, S is the actual sum, and S sub n we could think of as an estimate of that actual sum, because we're only adding up some of the terms. And so take the actual sum, subtract the estimate away, and R sub n would be the error in our estimate. Of course, S sub n would be our estimate, and R sub n would be the error, how far away we are, how much off we are, ARE. Now notice when we take all of the terms S and subtract the first n terms, S sub n, then R sub n is actually the sum from n plus 1 on. Because we're subtracting away the first S sub n, and that's the first n terms. And so R sub n is the sum starting at capital N plus 1 to infinity. Now, again, just to emphasize what I was saying, this R sub n is the amount of error in the approximation, where S sub n is the approximation. Now, R sub n could actually be positive or negative, because we're dealing with a alternating series here. And so we don't really know, because they're alternating in sign, we don't know whether capital S, the actual sum, or capital S subscript n, the estimate, we don't know whether either one of those are positive or negative. We just don't know. So we actually talk about the error being the absolute value of R sub n to be perfectly accurate with what we have to say here. And I thought I had another little piece to remember. Well, the statement is here, the statement is that this absolute value of R sub n, you can see, is less than or equal to a sub n plus 1, which says if we add up the first capital N terms, if we add up the first 100 terms, then the error that we have, R sub n, that's called the remainder, but we can really think of it as error. That remainder, or that error, is going to be less than or equal to whatever the 101st term is. So the error is always less than or equal to just the value of the next term in the series, not including the sign. Okay, that's a pretty significant statement. So here's the issue. Okay, I'm going to try to convince you of that in a moment, but for now, let's just look at it this way. That means that the difference between the absolute value of the difference between the actual sum and the estimated value of the actual sum, S capital N, sub capital N, is less than or equal to A sub, and that should actually be a capital N right here instead of a lowercase n. Which that means if the absolute value is less than or equal to the number, it means the what we're taking the absolute value of has to be between negative of that number and positive of that number. And so we know that S minus S subscript n is between negative A sub n plus 1 and positive A sub n plus 1. And if we take that expression and we add S sub n all the way through, it tells us that our actual sum, that's the value of the infinite series, lies between our estimate minus the next term and our estimate plus the next term. Okay, it lies between those values. And so that gives us a really powerful way to estimate the actual sum of a convergent alternating series. Now, what I'm going to try to do is convince you of this statement right here. Okay, R sub n is less than or equal to A sub n plus 1. And so first I want to point out to you that we don't know this capital N. We don't know, if it's even or odd, where it is. But what we do know, remember R sub n, let's go way back up here. R sub n is actually starting at capital N plus 1 and going to infinity because we subtracted away the first n terms right here. So R sub n is either going to start with a positive or it's going to start with a negative. If it starts with a positive, then it's going to alternate to negative and then to positive and then negative and then to positive. If it starts with negative, it's going to alternate then to positive, negative, positive. So, but it's starting at A sub n plus 1, and then we go to A sub n plus 2, and then A sub n plus 3, and so on all the way to infinity here. Well, let's consider this first case real quickly. If the R sub n actually is like this, here's what we can do. We can pair up, let's leave the A sub capital N plus 1 alone. Let's pair up beyond that the next two terms and then the next two terms. And notice when we add these two terms together, we're going to get a negative because remember, the A sub n's are getting smaller. So A sub n plus 3 is smaller than A sub n plus 2. A sub n plus 3 is smaller than A sub n plus 2. And here, A sub n plus 2 is being subtracted. So we're subtracting a larger number. A sub n plus 2 is larger than A sub n plus 3. So we're subtracting a larger number from A sub n plus 3. So we'll get a negative. Same argument here. We're subtracting a larger number from A sub n plus 5. Since these are getting smaller, A sub n plus 5 is a smaller number than A sub n plus 4. So this is larger. We're subtracting this larger from a smaller. So when we do that, we get a negative, and you can imagine that's going to pair up all the way through. So that tells us that R sub n has to be less than or equal to A sub n plus 1 because R sub n is starting with A sub n plus 1 and then subtracting a bunch from it. So it has to be smaller than A sub n plus 1, doesn't it? Okay, well, it's smaller than A sub n plus 1. Now, on the other hand, if our R sub n started with negatives, we'll start pairing up from the very beginning. And so we'll pair up A sub n plus 1 and A sub n plus 2. But remember, the negative is here, and this is a bigger number than this, so we end up with negative again. Just the same argument as above. But here, R sub n, clearly, we're adding a bunch of negative numbers together. So R sub n is the addition of a bunch of negative numbers. And so it's certainly going to be smaller than A sub n plus 1, isn't it? Okay. And so that's just a rough idea of why it works that way. And we're going to just accept the fact, though, this is really what we're accepting, is that the absolute value of S minus S sub n, that's the absolute value of R sub n, is less than or equal to A sub n plus 1. In other words, our error is smaller than the next term. That should be a capital N, as I said before. Well, let's move to an example, as you see here, to actually approximate. Here's the statement of the problem. Approximate the sum n equal 1 to infinity of negative 1 to the power n plus 1 times 1 over n factorial by its first 6 terms. So it just says add up the first 6 terms and use that as an approximation for the actual value. Well, I guess we should make a statement here that this series is in fact convergent based on the alternating series test. I'll let you verify that, but this is a convergent alternating series. So that's the first thing that's important. Now, S sub 6, that's the idea of approximating the sum with the first 6 terms. So we start at lowercase n, we go from n equal 1 to 6, and I've just listed those terms: 1 when n is 1, minus 1/2 when n is 2, plus 1/6 when n is 3, and so on. There's n equal 1, 2, 3, 4, 5, 6. And when we add and subtract appropriately, that comes up to be about 0.63194. I used my calculator for that. It wasn't difficult. So the 7th term, okay, now A sub n, it's actually not the whole term because we're just using this part of it. A sub 7, see, that would be the next term, wouldn't it? And A sub 7 then is 1 over 7 factorial. 1 over 7 factorial, which is 1 over 5,040, which is approximately 0.0002. And so we know that we're within 0.0002 when we use this number. We're within this amount. This number is within this amount of the actual sum. Well, let's play that out a little further. So our approximation, which is this, is within 0.002. That's where the A sub 7 came in, of the actual sum, just as I said. And so that means that the actual sum S is between S sub n minus A sub n minus A sub n plus 1 and S sub n plus A sub n plus 1. So in this case, we're using a capital N of 6. So our actual sum is between S sub 6 minus A sub 7 and S sub 6 plus A sub 7. And of course, S sub 6 is the 0.63194. And A sub 7 is the number 0.0002. And so we have that subtracted on this side and added on this side. And when we do that arithmetic, of course, then we get that S is between 0.63174 and 0.63214. With just using 6 terms, we know within that level of accuracy. And of course, don't forget that this S is the actual infinite series. So it represents the actual sum if we add infinitely. Well, let's continue this investigation with another type of problem. Similar but different. Determine the number of terms required to approximate the sum of the convergent series, as you see listed there, with an error of less than 1/1000th, 0.001. So we're assuming that the series is convergent by the way the problem is asked, is listed. So remember, since the error amount, the remainder, which is the error amount, if we take the absolute value of the error amount, it's always going to be less than or equal to A sub n plus 1. So we want our error amount, that's this absolute value, to be less than 0.001. So we want the n plus first term to be less than 0.001, and that would take care of it for us. And once we know what position that is, once we know n plus 1, we'll be able to tell what n is, and so we'll use we're going backwards. So we'll And that's all we're asked to do, is to find out how many terms. N represents the number of terms we need to use to estimate with. So here's what I've done. This isn't very sophisticated, and I mean, maybe not the best procedure all the time, but sometimes it works just fine. I started looking for a term, an a sub n, if you will, that was smaller than 0.001, because that's what I need, isn't it? And so I looked at a sub 0, what does that mean? I put as, oh, by the way, and it's hard to tell up here, but this is n equals 0 to infinity. Same procedures, no big deal. N equals 0 to infinity. So there is an a sub 0, and that's when you replace all the n's with 0 and you get a 1. And then I looked at the a sub 1s, okay, a sub 1, so that's when we replace all the n's here with 1, and I got a 1/2 or a 0.5. And I continued doing that. I might have jumped further ahead. I might have said, oh, let me jump clear over to here and try this. I got to a sub 4, and all I did was put a 4 in for my n's. So I had -1 to the 4th power. Excuse me, I stated this wrong. The a sub n includes everything but this -1 to a power, isn't it? So the a sub n is actually 1 over to the n power times n factorial in the denominator. So we don't include the negative. So when I'm looking at a sub 4, I have 1 over 2 to the 4th times 4 factorial, as you can see right here. That comes from this. And when I calculate that, I get 0.0026, which is still not less than this, 0.001. So then I tried a sub 5 finally. And when I did and calculated a sub 5, I got 0.0002604, and this is in fact less than 0.001. And so I feel like I hit pay dirt. From that information then, a sub 5, which is this number, is less than or equal to 0.001. And remember, at least the absolute value of r sub n, I should have put here, is less than a sub n plus 1. So I'm looking for n actually, and because of this, I know that the a sub n plus 1 I'm looking for is actually a sub 5. When I finally found a term that was less than my error, then that's the n plus first position. That's the n plus first term. And so a sub 5 is my 5 is my n plus 1, and so n has to be 4, which is telling me that I need to add up the terms from 0 to 4. Remember, this started at 0. Well, okay, then remember what we were actually, let's not forget what we were trying to do. So let me scroll clear back up here. Determine the number of terms required to approximate the sum of the convergence series with an error of less than 0.001. Well, actually the number of terms, because I have to go to 4, the number of terms is actually 5, see, because we're starting at 0. But 1, 2, 3, 4, 5, 0 to 4, and that's what we found. Now, I went a little further. That's all we were asked here. We should have said we have to add up the first 5 terms. But I went ahead and added up the first 5 terms, and when I did, I got approximately 0.607. Okay, so the original series, the infinite sum, is approximately equal to this amount, which we've ensured has a smaller than a 1/1000th error. That's what all of this was about. If we use the first 5 terms, then our error will be within 1/1000th of the actual series. Okay, and in fact, in this case, the actual sum, the infinite sum, actually ends up being 1 over the square root of e, and that's approximately 0.6065306. So you can see to this position, we are no further off than 1/1000th to this position, because this is actually within what, 5/10,000ths of this amount. So, and we did that with just 4 terms. Well, the next problem is similar to this, but it's a little, we use a little more algebra in the process. Let me put up a screen so that we don't see everything at once. and we see everything, it's kind of hard to focus, I think. We're to determine the number of terms needed to approximate this alternating series with an error of less than 1/1000th again. And so, as we did before, we're wanting to make sure that the capital N plus 1 term is less than 1/1000th, because the error will be less than this N plus first term. By using, the error is less than this term when we approximate with N terms. Hard way to say that. And so all I've done here is I've replaced a sub n plus 1, which, remember, here's a sub n. So I've replaced a sub capital N plus 1 with what it's equal to, and that's 1 over capital N plus 1. And then just a little algebra. I didn't show all of the algebra here, but you would write this side as a fraction 1 over 1000, and then I'd be multiplying back and forth until I got 1000 is less than n plus 1. And I just happened to turn that around and say n plus 1 is greater than 1000. And so I subtracted 1 on both sides, and I got n is greater than 999. Now remember, capital N is an integer, and so if we have an integer that's greater than 999, the first integer, the smallest integer it can be to be greater than 199 is 1000. So we need to add up 1000 terms to be within an error of 1/1000th of the actual sum. That's what that says. It takes the first 1000 terms to get within 0.001 of the actual sum. You know, in the last problem, we just had to add 5 terms to get within 1/1000th. And so in that case, we say it converges very quickly. Here, it converges very slowly. You know, we're not getting a great deal of accuracy without having to add a lot of terms. Let's see what else we have here. What I went ahead and did here, just to show you an example, the actual infinite sum comes up to be the natural log of 2. And the natural log of 2 is approximately 0.69314778. If we add up the first 1000 terms, okay, it would look like this. And of course, they're alternating in sign. And if I add up those first 1000 terms, and I can't tell you that I did that with my calculator, I used something fancier, but I got about 0.693. Oh, okay, well, it matches the first 3 terms here, doesn't it? The first 3 decimal places. So this going 1000 terms gives us a reasonable accuracy, and certainly we're within 1/1000th. The question just asked how many terms, and so the answer here would have been 1000. Well, I hope this gets you started real well on the homework where you have to approximate or do things with the remainder. This is called the remainder theorem. So good luck on your homework.